So today's lessons on cations and anions represents the first official lesson in grade 10 chemistry. However, having said that, the word cation and anion should be familiar to you, as you definitely learned about it in grade 9, but we're just going to extend upon it this year. But before we get there, I want to talk about some important ideas relating to the atom. Okay, so first, you need to understand that atoms will gain or lose electrons to become stable. And that's actually why chemical reactions happen. It's in an effort for those atoms, or atoms within a molecule, to become stable. Okay, and so atoms are most stable when their outer or valence shell is full. And so, having reviewed Bohr-Rutherford diagrams, we know that for a shell to be full, it depends on which energy level we're talking about, right? In that first energy level, we have 2 electrons max. Okay, so 2 would mean full. And in every energy level thereafter, for our purposes, we're going to look at 8 electrons as helping to make that valence shell full. Okay, now it's important to note that in chemical reactions, the electrons are going to be gained or lost. We don't touch the protons and we don't touch the neutrons in chemical reactions. Chemical reactions involve simply the losing and gaining of electrons. Okay, so that's the first piece. The second piece is that atoms are electrically neutral. And as we discussed in the review, we consider them to be electrically neutral because they have the same number of positive charges, or protons, and negative charges, or electrons, right? So the positives, if the number of positives equal the number of negatives, they kind of just cancel each other out. Okay, so what we're going to do is we're going to look at hydrogen. And hydrogen in science is often used to model because it's the smallest and simplest element. And so it kind of forms a good basis for starting to understand properties of the atom. Okay, so let's break down some of the details, and this will serve as a good review. Okay, when we're looking at the number of protons, electrons, and neutrons, we can get that information from the periodic table. Okay, the atomic number is telling me that I have 1 proton, 1 electron. And then, this mass number of 1 minus 1 tells me that I have 0 neutrons. So yeah, in fact, hydrogen has 0 neutrons. Okay, so it's super, super light. So here I have this Bohr-Rutherford diagram of hydrogen with its 1 lone electron in that first energy level. Now I know that energy level can, we can add or take away electrons from it. So is this atom stable? Right? Is this hydrogen atom stable right now? Well, no, because I can add another electron here, right? And so when an atom gains an electron, we know that it becomes negatively charged. So at this point, I've added an electron because now this outer shell is full and this particular atom would be more stable. But as soon as I did that, I set off the balance of protons to electrons, right? I now have 1 extra negative charge compared to my positive charge, right? So, before I would have had 1 proton, now I have, and 1 electron, now I have 2. So we can kind of think about this like adding integers, right? Where I have 1 positive charge and 2 negative charges, giving me an overall charge of -1. Okay? And so in doing that, I don't have an electrically neutral atom anymore. I have something different. Okay, now when an atom loses electrons, it becomes positively charged, right? So remember how we added an electron to hydrogen to make sure its outer shell was full? Well, we could just as soon take away that electron, and then it would have no shells and thus gain stability by losing its 1 electron. Okay, and so when it does that, let's do the math here. Well, I have, that electron's gone. What do I have left? Well, I have 1 proton and I have 0 electrons now. So since I have a positive charge and no negative charges, the only charge contributing to the electrical bit is that positive charge, right? And so overall, this would be a particle with a positive 1 charge. Now, each of these negative and positive charges have names, okay? But generally speaking, we talk about any atom that has lost or gained electrons and that has now an electrical charge, we call that an ion. Okay, and we can have positive ions and we can have negative ions. Okay, so two types. We have our cations and we have our anions, and you may already be remembering what the difference is between those, which one is which. So let's get to that. So cations, I think about like a cat, right? Like the animal cat and its paw. Okay, so cations are positively charged due to the loss of electrons. Right? So we have to add electrons for that to happen, or sorry, we have to add energy for that to happen. Let's take a look. Okay, so what I want you to imagine here, well, let's take a look at this. This happens to be a sodium atom. And, you know, when I look at the Bohr-Rutherford diagram of a sodium atom, well, what do I notice about it? I notice that it's not stable. Right? How do I know that? Well, it's got this one electron in its outer shell. And so that outer shell is not full. So it can do a couple of things, right? I know that 8 electrons can fit in that shell, but right now there's only 1. So is it easier for this atom to gain 7 more electrons to fill its outer shell? Or is it easier for it to just lose that electron? Well, I think it's easier to lose 1 electron. Okay, but remember that that positive nucleus is attracting that negative electron. So we need to use the energy to pull off that electron from our sodium atom. Okay, it's not too hard to do because it kind of wants to lose it anyway. But when we do that, notice that what we get is we have an ion with 1 less electron and 1 less energy level. So the atom actually shrinks in size. Right? And so now that electron's kind of like roaming free on its own, ready to do some work in other places. Okay, so we add an energy to take that electron off, and then we create this really stable sodium ion. So another way to represent that would be to say we're going to take our sodium ion, add energy, and then we end up with our we're going to take our sodium atom and then create our sodium ion. Okay, so if we look at the charges, we know that a neutral atom will have the same number of protons and electrons. And in this case, now what I've created is I've created a situation where I've taken away an electric charge. So I have, you know, an overall positive 1 charge. Okay, that makes this a cation. Okay, so let's talk about elements in group 1. So group 1 elements will all have 1 valence electron, okay? And they easily form cations because of that 1 valence electron, okay? They're super chemically reactive as a result because they all want to lose that electron to become stable, okay? And so that's what they do, okay? And so we know that reactivity, as we move down a group here, is going to increase. And it's going to increase because that outer electron becomes further and further away from the nucleus. And so the pull of that positive nucleus becomes less and less. Okay? Now, so essentially, the further a valence electron is from that positive nucleus, the easier it's going to be to pluck it off. And if the easier it is to pluck off, that's really just an indication of its reactivity. Okay, if it's going to happen more quickly, that means it's going to be more reactive. Okay, let's look at this second group here. And, you know, maybe you remember from grade 9 what that group is called. I'm going to remind you, it's called the alkaline earth metals. Okay, they also will form cations, but they have to lose 2 electrons to do that. Okay, and in order to lose those 2 electrons, that's going to take some energy as well. Okay, but they're going to be less reactive because removing 2 electrons is going to be a little bit harder and a little bit slower than removing 1 electron like we saw with our alkali metals. Okay, and that's it. Okay, so there's going to be a stronger attraction to the nucleus because, you know, as we move across here, these elements are going to have more protons in their nucleus, but they're also going to have to remove more electrons. Okay, so let's look at that in a little bit more depth. So let's take a look at, well, what do I have here? So I would look on the periodic table and look for the element with 12 protons. Okay, take a minute to figure out what element I'm looking at here. Hopefully you can recognize that this is a magnesium atom. Okay, and so let's take a look at the difference between these. Well, is this guy stable? Hopefully you said no. Why is it not stable? Well, it's got these 2 electrons in its outer shell. It does not want those. And its options are to gain 6 more or to lose 2. And so easier to lose 2. When it loses those 2 electrons, we see that outer shell gone. But then it has, you know, instead of having 12 electrons, it only has 10 electrons, right? And so what we create here is a magnesium cation, and then the 2 electrons are, you know, somewhere else doing other work. Okay, so looking at the overall charges, we have 12 positive protons and 12 negative electrons initially, which is what makes this magnesium atom neutrally charged. But when we take those 2 electrons away, right, we end up with, you know, 2 fewer electrons or negative charges, which gives this atom now a positive 2 charge and makes it a cation. Let's talk about anions now. Now, at this point, I'm sure you got to the place where you're able to kind of predict that an anion is a negatively charged ion, okay, and that it becomes negatively charged because it's going to gain electrons, 1 or more. And so when that happens, you know, usually that makes the atom more stable and happy, and it kind of just goes, and it releases that extra energy. So energy is released when electrons are gained, typically. Okay. Now let's take a look at what we have here. So I have fluorine, and hopefully you have your periodic table in front of you and you can locate fluorine on the periodic table. So take a minute to do that. Okay. Now fluorine, if you were to look at its Bohr-Rutherford diagram, you would see that it has 9 protons and 9 electrons. And so in that outer shell, it has 1, 2, 3, 4, 5, 6, 7 electrons. And it's not happy right now, right? It's not stable because it wants to have a full outer shell. And so its options are to gain 1 other electron to fill that outer shell, or to lose all 7 that are in that outer shell. So energetically, it's going to be easier for it to gain 1 electron, you know, because the positive nucleus is holding in all those other electrons, right? So losing 7 would take a lot of work. So it gains the 1 electron, and then its outer shell is full, right? And it becomes stable and it releases energy. Now, looking at the charges again, we know initially it was neutral because its number of positive and negative charges were the same. But now, since it's gained an extra negative charge, instead of having 9 protons, it has, or 9 electrons, it has 10 electrons, giving it an overall negative 1 charge, making it now an ion. Okay, so question, what do we call the elements in this particular group, right? In this particular family? Hopefully you remembered that they are halogens. And the halogens, we would say, are super reactive as well because they all have 7 electrons in that valence shell, in their outer shell. Okay, so they want desperately to get that extra electron to fill their valence. Okay, and so we know that as we go down a group, atoms are gaining more and more electrons, you know, and so that the valence electrons for this guy, let's say, are going to be much further away from that positive pull of the nucleus. And so electrons over here, you know, for this guy to grab onto an extra electron is going to be a lot harder because the pull's not as great. It's kind of like magnets, right? So fluorine we can think of as being a really strong magnet because its nucleus and its valence shell are really close together, right? And the closer we kind of move magnets to each other, the kind of stronger that pull is felt. But, you know, if the magnets are far apart, right, like the positive nucleus and the negative electrons are far apart, then it's going to be really hard for this guy, acetine, to grab onto an extra electron and pull it towards it. Okay, so the further a valence electron is from the positive nucleus, the less easily it can gain the electrons and the less reactive the atom is. Just to sum it up. So let's talk about, in this case, let's talk about sulfur. Okay, so sulfur, it has, let's look at its outer shell. 1, 2, 3, 4, 5, 6 valence electrons. Okay, and it's not happy because it doesn't have a full outer shell. And so again, it can lose 6 electrons, or it can gain 2 to get 8 in its outer shell. Much easier for it to gain 2 electrons. When it does that, it gains 2 extra negative charges, making it an anion with a -2 charge. Okay, and so, initially we have equal charges, equal positive and negative charges. By the time that sulfur atom gains its 2 extra electrons, right, it has an overall -2 charge. Okay, so oxygen, the oxygen family, sometimes called, I believe, the chalcogens, will have to, they're going to form anions, but they have to gain 2 electrons to do it. They're going to be less reactive because it's going to be harder for oxygen and sulfur and selenium and so on to gain 2 electrons. That's harder. And also they have fewer protons in their nucleus, so harder for them to pull the electron towards themselves, right? They're just like a weaker magnet. Okay, so after the first electron is gained, the anion is already negative. The like charges are going to repel, and, to grab onto another electron is going to be pretty hard, right? So that's the message there. So cations, positively charged. Anions, negatively charged. Cations we form when we have electrons removed, and because there are more protons than electrons. Anions we get when we add electrons to an atom for it to be stable, making it negatively charged. Okay, so anions are given the ending "ide." Okay, so for instance, the sulfur atom becomes the sulfide ion. We wouldn't say the sulfur ion, we would say the sulfide ion. Okay, in the same way, an oxygen atom, when it gains 2 electrons, will become an oxide ion. Okay, so that happens only with anions. It does not happen with cations. Cations will keep their name. We're going to see how this becomes important when we get into naming chemical compounds a little bit later on in this unit. Okay, now we're going to all graduate to what is called the electron dot diagram. So at the end of this video, we should have consolidated some of the trends that we see in the periodic table. And so knowing that only the valence electrons are being gained or lost, we're not going to worry about Bohr-Rutherford diagrams anymore. We're simply going to know the trends that in every element in that first group has 1 valence electron. Every element in group 2, the alkaline earth metals, will have 3. Now we're skipping over the transition metals in between here, folks. We do not touch those until grade, I want to say 12 mostly. Okay, so we're skipping over them. Locate on your own periodic table where boron is, just for reference sake. Okay, so as we move across those groups, 1 valence electron, 2 valence electrons, 3 valence electrons, 4, 5, 6, 7, and now here are the noble gases with their full outer shells. Okay, so what we have now is what we call these electron dot diagrams. We're going to not use our Bohr-Rutherfords because the valence electrons are the only ones that are typically involved in reacting. Okay, so much more convenient, a little bit quicker. So expect to see that in upcoming videos. And make sure you know these trends so that when we look at a Kahoot tomorrow, you'll be able to identify that. So that's it for this video, folks. If you have any questions, again, at every stage in this chemistry unit, it's going to be really important for you to consolidate and understand the ideas because they provide the foundation for everything else. So invest in understanding this. This is a longer unit, and so we're going to want you to be successful throughout. So reach out and clarify if you have any questions, and I'll be happy to help you out.